Thank you for your very generous introduction, and I can't tell you how delighted I am to be with you here this evening. I hope you appreciate the efforts we went to engineer the kind of weather to put you in the mood of talking about hurricanes. We've been experimenting with weather modification at MIT, and weren't sure we could pull it off, but I think it worked. It seemed to work, so well, maybe it's just beginner's luck. What I want to talk to you about tonight is not just hurricanes per se, which is something I've been fascinated with since I was a child, and I'll tell you something about their physics and how they behave, but how today we're using what we've come to understand about the science of these storms to actually go about trying to assess the risk of them. So, for example, wouldn't you like to know how probable is it that you're going to get a Cat 5 hurricane in Pensacola? Is that something that happens every 50 years or every 200 years on average? And we also like to be able to do that not just for today's climate, but for the climate that our children and grandchildren will experience, which will be different, if for no other reason that the sea level is going up, and that will change the incidence of flooding from storm surges. So let me tell you what we have in mind tonight. This is just an idea about the program. I'm just going to start off with a brief overview of hurricanes. I think probably a lot of you know about hurricanes a lot already, so I won't spend a lot of time on that. A little bit about the theory of hurricanes. And I realize that at this time of the evening it's not wise to spend a lot of time talking about theory, so there'll be 1 or 2 slides on it. And then how do we apply theory and the science of hurricanes to assess hurricane risk? That's basically the 3 things I'd like to cover tonight. So let me begin with the overview. Now, I've switched terms on you, right? Now I'm talking about tropical cyclones, and I'm going to go back and forth between those. So I should let you know that tropical cyclones, the generic term that we use in atmospheric science for these storms, no matter where they occur on the planet. And I'll tell you in a minute about where the word hurricane came from, in case you don't already know what's a hurricane. If you look up in a dictionary or a meteorological glossary, you'll see that hurricane is a variety or a local name for this generic term, tropical cyclone. It's a tropical cyclone with 1-minute average winds at an altitude of 10 meters exceeding about 74 miles per hour, occurring over the North Atlantic or eastern North Pacific. So this is a regional term. The generic term tropical cyclones used all over the world. Only about 11% of the world's tropical cyclones occur in the Atlantic, but the Atlantic storms get about 98% of the press. So you should remember that. Now, the word hurricane is derived from very similar sounding words like Huracan and Unraken, who were all sort of gods of evil of the tribes, the pre-Columbian tribes that inhabited the region around the Caribbean. So the Taínos, the Caribs, and the Mayans all had this word. And it was brought finally to the West by the early Spanish explorers, including Columbus himself, who experienced a hurricane during his 4th and final voyage to the New World. Now that image that you see in the lower left is an image of Huracan lifted off of an ancient Cuban vase from the pre-Columbian times. And you see many images like this, and I think it's fascinating. You've got this sort of spooky looking skull, and instead of ears, you have these spiral arms. Not only are they spiral arms, but they're spiral arms whose sense of rotation is correct for a northern hemisphere hurricane. That's very interesting to us because we arrogant Western scientists think that we didn't discover that hurricanes were rotating vortices until the middle of the 19th century. And there are indications now that these ancients knew that they were rotating storms many, many centuries before that. In fact, the folks who invented the symbol that we put on weather maps today to denote the presence of a tropical cyclone, what you see on the right there, probably had no idea about those images from the ancient Cuban vase. You can see the similarity. There is I just happened to go to Tulum last fall and took this picture of the Temple of the Winds. The Mayans learned to build their cities inland away from hurricanes, except for Tulum, which was one of their last major cities. They moved to the coast in desperation because they had exhausted the soils of the interior of the Yucatan. And the first thing they did was build this temple to try to placate the hurricane gods. It didn't really work. Now, you've all seen pretty pictures of hurricanes from space. Here is one of Hurricane Floyd approaching Florida, which you see there in the upper left. And it didn't hit Florida, it went into the Carolinas. But when you look down from space, you see this swirling mass of clouds a few hundred miles across. The thickest clouds, the heaviest rain, and the strongest winds are in an annulus, like a donut, that surrounds an eye, often free of clouds except in the very base. And when you look down from the top, you're seeing clouds that are up about 12 or 13 miles above the surface, where the temperature is well below, get this, well below minus 100 degrees Fahrenheit. These are all made of ice up here. The top of a hurricane is one of the coldest places you can find in the whole planet, including Antarctica. Okay? Of course, it's very warm at the surface. Now, just zooming in, here's a photograph from the International Space Station of Hurricane Igor of 2010. And you see this, again, this close-up of the eye wall. This is basically an array of thunderstorms, not too dissimilar to what we just experienced, but they're in this ring. Under this ring is where the very strong winds occur, and then here's the eye of the storm. The interface between this annulus and the eye is referred to as the eye wall. And you'll see in the next picture why we call it an eye wall, or next picture after this. Since the 1940s, when a very daring instructor from Texas flew a small airplane into a hurricane for the first time, we've been flying into Atlantic hurricanes pretty routinely using aircraft like these P-3 Orions, which are very strong. And I have done a number of hurricane flights myself, mostly in the course of doing research. And when you fly into the center of a storm, this is why you call it the eye wall. This is what you see. And no photograph can possibly do it justice. It's like standing in a football stadium with white sides rather than being 100 feet high, 12 miles high, and maybe 30 or 40 miles across. And you just can't convey that in a picture. This is the blue sky of the stratosphere. There's sometimes a cascade of ice crystals falling down the inside of the eye wall. And the base of the eye is usually filled with low clouds not very far off the surface of the ocean. So I think this is so spectacular that when I retire, I'm planning to start a hurricane safari. I think everybody should see this. So if you want to sign up, let me know. Just a word about the climatology of tropical cyclones. This is just a map showing the tracks of these storms from 1945 to 2006. And the colors, if you look at this down here, show the Saffir-Simpson category, basically a measure of the strength of the winds. So these are the storms that you are all familiar with for sure, that form off of Africa, anywhere from off of Africa to the Gulf of Mexico, generally track westward and northward and then curve up. Some of them that don't make landfall curve up to the north and east. Even we get the odd hurricane in Boston, where I live. There's another very active belt off the west coast of Mexico. These storms form just off the coast and move westward and rarely affect land, but one did this year, Patricia, which was the strongest hurricane ever measured in either of these two basins. That just occurred this past fall. Sometimes they influence Hawaii. And then there's a very, very active belt in the western North Pacific. These storms also track westward and curve north, affect anywhere from the Philippines to Taiwan, China, Vietnam, Korea, Japan, and so forth. And in the Bay of Bengal, in the eastern Arabian Sea, has storms as well. And there's a belt in the southern hemisphere from the central Pacific across northern Australia, all the way across the southern Indian Ocean to Madagascar, Mozambique, and so forth. And you'll notice some interesting things. There's one storm on record in the South Atlantic. There it is, if you have good eyesight. And there are no storms within a few degrees latitude of the equator. So if you want to sail a boat around the world and you're afraid of hurricanes, you just stick to the equator and you'll be fine. Of course, you might have other problems, but you won't have that problem. Hurricanes are creatures of the late summer and early fall. This is just the number of storms in the northern hemisphere per month. So you read the month off this upper axis is going from January to December. So the peak in the storms are August, September, October, as you know. It's certainly true here, but in the southern hemisphere, they're also creatures of the summer, more like the midsummer. So you read it off this scale down here, which, of course, in the southern hemisphere is December, January, February, thereabouts. Okay. There are some storms in the winter of each hemisphere, but not many. Let's talk a little bit about theory, and I put in one slide for the engineers and scientists in the audience. The rest of you can have a very short nap, okay, if you don't like this sort of thing. But I find it fascinating. It's what I spend my time. This is a cartoon through a hurricane whose center is right over here on the left. So this is altitude. It's actually in kilometers. This is about 10 miles, 16 kilometers. And then this is distance from the center out to 200 kilometers, about 120 miles or so. And this is a cartoon that I drew myself, not very competently, of the eye wall cloud. This is the eye of the storm. And the lurid colors you see on this diagram are a measure of the heat content of the air. So for the engineers, this is the entropy of the air and the water vapor and condensed water in it. And the only way you can change this quantity is by transfer of heat from the sea or transfer of heat by radiation into space. Okay? Now, supposing you were so unwise as to go for a hot air balloon ride, starting at A, please don't try this at home, you would be sucked into the vortex, you'd be spinning wildly around it, but you also would be going in toward the center. And when you get to the eye wall, if you've survived that far, you'd be shot up, the strong updrafts of the eye wall, and you go out, and then over a period of many weeks, you return back down to A, ideally. Now, you'll notice that this heat content, the blue is low, the red is high, is going up, and that reflects what's really driving the hurricane. It's not that hard to understand. It's transfer of heat from the ocean to the atmosphere, which occurs when seawater evaporates. That's what drives the hurricane. That's the boiler room of the hurricane. That's why they immediately begin to dissipate when they move on land or over cold water. Then the air goes up lines of constant color or constant entropy, and all that heat that you got from the sea is slowly lost by infrared radiation to space. So it's lost up here and it comes down. Now, what's really remarkable about this, and again, this is for the engineers in the room, is that this is the four legs of a kind of cycle for converting heat energy into mechanical energy, which is the most efficient that's theoretically possible, as discovered in the middle of the 19th century by the French thermodynamicist Sadi Carnot. This is isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. And that is why these storms are so violent. They're the most efficient engine you can think of for turning heat energy into wind energy. And the efficiency of that engine depends on how different the temperature is between the ocean surface where you're putting in the heat and the high atmosphere where it's finally being radiated to space. And that difference is enormous. And remember, I told you how cold it was at the top of the hurricane. So it's almost diabolical. And you have the most peaceful climate on Earth, as you all know, because you live in one here, the tropics. Nevertheless, ironically, subject to the most violent storms on the planet. Now, we can put numbers on this, and no, I'm not going to do that for you, theoretically, but this is a chart based on the theory showing the theory gives you a speed limit on how strong hurricanes can be in a given climate. And this is the speed limit of the winds in miles per hour. So the deepest reds are about 200 miles per hour, which do correspond nicely to the most intense winds measured. And you can see that they're confined to the tropics. And here in the Gulf of Mexico, you can get up to about 180 miles per hour and so forth. And then as you go out of the tropics, basically you can't have any hurricanes at all. Now, hurricanes can move rapidly out of the tropics and still do damage before they've had time to dissipate, but they can't form in these blue regions. All right, so now let's turn to the subject of risk. And this is probably the most practical side of this evening's talk, is how do we actually go about doing this? And we made a lot of progress in the last 10 years on this. So let's first of all talk about what are the risks. Well, the one everybody thinks of, and the most obvious one, is just wind, right? The wind's blowing 150 miles an hour. The force of the wind goes as the square of the wind speed. So you know it's kind of hard to stand up in a 40 mile per hour wind. You can do it, but it's not easy. If If the wind goes to 80 miles an hour, which is a weak hurricane, that's 4 times the force on your body. Twice the wind speed, 4 times the force. Most people can't stand up in a wind like that. And then think of what it's like if it's 180 miles per hour. There's no way, right? So wind, as you know, does a lot of damage. Buildings today are designed to tolerate winds up to, say, weak hurricane force, but not much beyond that usually. The other risk, another risk which is not often talked about, but which actually is more serious historically, is rain. Why is rain risky? Because it leads to freshwater flooding. In 1998, Hurricane Mitch went into Central America and killed 12,000 people. 12,000, all from freshwater flooding, none from wind. Okay? So we worry a lot about rain. It's not as sexy as wind. You don't see Weather Channel reporters standing out in a drenching rainstorm telling you how exciting it is to be there. Or at least I haven't seen that. All right. Now, the real killer, though, is another kind of flooding caused by something called the storm surge. This is what did in New Orleans and in New York City with Sandy. Now, the problem with that term is everybody's heard it. Not very many people can visualize it. You know, what is it? Is it a big wave? So I'm going to show you a film, if I can get it to go, of a storm surge shot by a very lucky man in the middle of Typhoon Haiyan, the strongest typhoon on record in the Western Pacific just a few years ago. All right, so let's see if I can get that to work. Just watch, okay? This is out the window looking at an adjoining house. All right, that's a storm surge. Now you know you can't survive that, right? It's the same thing as a tsunami. It's hydrodynamically the same thing. It's just that it's caused by wind rather than shaking seafloor. And you can't outrun it. There's nothing you can do, all right? This is the big killer. It is a tsunami that arrives typically in a hell of a windstorm, all right? And it is historically, a storm surge killed 500,000 people. One storm surge in the Bay of Bengal in 1970, which caused what was then East Pakistan to become Bangladesh, had that much reverberation politically. Here in the US, if you look at damage by all kinds of different weather phenomena and other things like wildfires, this is just a pie chart showing this, and you can see that most of the damage, this blue, is caused by tropical cyclones, aka hurricanes. And then there have droughts, and then you have severe storms like we had today, thunderstorms, non-tropical floods, winter storms, wildfires, freezes, all right? So the insurance industry is understandably extremely concerned about hurricanes, for example. Now, how are we going to actually go about assessing risk? And I want to talk to you about some old ideas and some new ones. I'm actually going to start off with a pretty new one. It's a relatively new field. It's called paleotempestology. And my only contribution to that entire field was to give it its name. It's probably the only word I've ever come up with which you can find in the dictionary. It's trying to find evidence for ancient hurricanes in the geological record. Now, here's how, there are several different techniques. I'm going to talk about one which is relatively easy to understand. So often when you have the sea over here on the left, or the Gulf of Mexico, that's separated from the actual mainland by a barrier beach, and the inland of which you typically have a marsh and or a lagoon. You see that all along the Gulf Coast, along the west and east coasts of Florida, the Carolinas, and so forth. Now, in the lagoon and the marsh, you just have stuff growing and dying, and when it dies, it becomes mud and so forth, and it's just a long cycle, continuously building up layers of mud. When a storm surge comes in, it will wash sand into this marsh or lagoon and leave these layers of sand. So you can fill a rubber dinghy, as my colleagues do at Louisiana State University, with graduate students who have a coring device, and you can take a core through this. And you can use modern radiocarbon dating techniques to find out how old the mud is adjacent to the sand, so you can figure out when the sand layer happened. And you can go back several thousand years, which is well before history with this technique. And that's been done all around here, although not here in Pensacola, But for example, a colleague of mine, I was involved in the study, did a study in a back barrier pond and a bunch of sinkholes inland from a place at the head of Appalachia Bay to our east here. Okay, I'm going to talk about some of those results. And here we are. So this is a graph showing what they discovered at the head of Appalachia Bay. And here's how you read it. This is time, and this is AD or BC. So this is 2000 BC on the left, going to the present, more or less, 2000 AD on the right. These spikes correspond to how coarse the material was in the core. And the coarser it is, the more likely it is to be sand, and that demarks hurricanes. And we know from the very end of the record, they correspond to well-known actual historical events that are recorded historically in the region, like Hurricane Dennis, Hurricane Elena. And then this spike, which is in about 1780, might have been what's a famous event in Spanish and American history called Solano's Storm. Some of you may have heard about that. It wrecked one of the Spanish fleets. Now, when you go back to the left of this is before history. And you can see something interesting. I mean, of course, these are pretty irregular, but you could see periods of time, like from 500 to maybe 1400 AD, when there are a lot more storms than there are today. And then there are other times back here from maybe 300 BC to 400 AD when there weren't, more like today, there weren't very many storms. And then this very active period. So we're learning a lot about how hurricanes respond to climate change, in this case natural climate change, by this technique called paleotempestology. And there's a lot more to it than I have time to tell you tonight, but I thought I'd at least start with that. Now, the other thing you can do is to use historical storms and try to make sense of those. This doesn't work very well. Yet, your insurance rates that you're paying if you're a homeowner, and indirectly if you're a renter, okay, are based upon what I would regard as very flimsy statistics. Let's talk about that. So here is a chart that was compiled by my colleague Roger Pilkey Jr. and Chris Lansey, who's at the National Hurricane Center some years ago, showing the total amount of damage done in 2004 dollars by hurricanes in the United States over the period 1900 to 2004, correcting for changes in wealth and population over the period. And it's categorized by the Saffir-Simpson hurricane category. So these are the weak storms, category 1, category 2. This is category 3, category 4, and category 5. So most of the damage is done by 3s and 4s, okay? But if you look at the number of events, most hurricanes that make landfall are category 1. And then there are some category 2. There are a few category 3. There's been maybe 10 category 4 hurricanes at landfall in this whole century, and maybe 3 category 5. So but go back to the previous chart. All the damage over this 100 years has been done by a handful of storms that swamp all the other ones in terms of the amount, like Katrina. Katrina is by far the most expensive event we've had by any measure. There just aren't very many of them, all right? And yet your insurance rates are based upon a tiny number of events. And that's for the whole US. If you want to look at Pensacola, forget it. I mean, the statistics of any small place are just, there's virtually nothing to go on. So to summarize, this is just from the statistics, more than half of all the US hurricane damage has been caused by 8 events in our history. 8. Now, I don't know about you, but most statisticians would look at 8 and say, not going near that one. It doesn't stop the insurance companies from doing that. And they were all high category events. More than 90% of the damage is caused by storms of category 3 and greater. But they are only, 3, 4s, and 5s are only 13% of the total. And there have only been 30 of those events, 3, 4, and 5 at landfall since 1870. So we can conclude that landfalling storm statistics, historical statistics, are just plain inadequate for assessing hurricane risk. This is a big problem. This is where I hope science can come to the rescue and make the insurance actuarial statistics much more robust, which may mean that your insurance rates go down, but it might also mean they go up. So I'm going to hide after this talk. I don't know. Some places they'll go down, some places they'll go up. So what are we going to do about this? Well, we could try to use hurricanes simulated by global models, okay? Computer hurricanes, if you will. There's a problem with that. It's a bit subtle, and it just has to do with the fact that today's most sophisticated global models just don't resolve hurricanes very well. Their computational points at which the computations are performed are typically 80 miles apart, and that's just way, way too low. So if we look at the number of storms in a very, very fancy global model, one of the best you could possibly find today with 30-mile grid spacing, it's much better than the ordinary model. Look at the number of storms by wind speed. This is the red curve. There are lots of weak storms. This is in meters per second. Sorry about that. You have to double it to get miles per hour. This black line is the division between Category 2 and Category 3, so all the damaging storms are to the right, and they don't simulate any of the damaging storms at all. They just can't do it. The black is what we observe, all right? And again, it's still most of the storms are weak. It's these out here in the tail that do most of the damage. So global models can't do it. So at MIT, we said, okay, well, let's see if we can get around this. We're going to take the global model and we're going to embed within it a really good hurricane model. It's very, very detailed, has very fine resolution, it's coupled to the ocean, all kinds of things that I love, bells and whistles that I won't bore you with. And yet, the model is simple enough that in a given climate, we can easily generate 100,000 storms. Now you're talking Turkey with statistics, right? 100,000 is a whole lot better than 8. So, for example, here are the tracks of hurricanes simulated by the MIT technique. This is a mere 1,000. If I tried to put 10,000 on here, it'd just be a complete mess. It's already a bit of a mess. Those of you who are hurricane fans will probably be able to look at this and make some sense of it. Again, the colors have to do with the Saffir-Simpson category, but we subject these to much more rigorous statistical tests against historical events than just looking at a chart like this. We even got two storms in the South Atlantic here. So in preparation for this talk, I thought I'd run this technique by filtering storms that pass within 150 kilometers, roughly 100 miles of where you're sitting right now, all right? So it's fairly easy to run this. So we generated 200, we generated about 3,000, but I can't show you all of those. These are 200 randomly chosen events that happen to pass within about 100 miles of here. And if you can make the distinction of these purple or red curves here, those are all the historical events in the record that also pass within 100 miles of Pensacola. And this includes Ivan of 2004, which I'm sure many of you remember was a very destructive storm, but by no means the most intense you could have here in Pensacola. So here is just taking one of those events. This is the track of the event. It came up from off the west coast of Florida, went inland just east of here, and then these contours show the peak wind experienced at any point as the storm went by. In yet another unit, sorry about that, nautical miles per hour. Boaters will know what that is. It's a little bit more than a statute mile per hour. And so this one produced pretty strong winds near Pensacola, about 150 knots. That was a pretty strong event. So we can do a lot of statistics with that. This is the same thing, but for rain. The model also produces rain. This one was a whopper. It produced, in this area here, 700 millimeters. That's 70 centimeters. That's a lot of rain, okay, during the passage of the storm. That would have caused a lot of freshwater flooding. And so we can do statistics. And we can look at return periods, which is just the average interval between events, as a function of how strong they are. So you read the return period off this axis and the strength of the winds at landfall off of this. This is for storms passing within about 100 miles of here. And the green dots are what you could derive from historical data, and the blue dots are what you can derive from a fairly limited number of these modeled tracks. And you don't have to focus too much on these dashed lines, but they show you the probability that the historical event should lie within the synthetic events if they were drawn from the same distribution. So a storm the size of Ivan, which was about 125 knots at landfall, is something that, based on this technique, you might get once a century. So Ivan was, we think, about a century, 100-year storm. All right. So, you know, how probable is a Cat 5? Well, Cat 5 is up a little bit closer to 400 knots. That's many, many centuries. You'd have to wait to see a Cat 5 within 100 miles of here. That's the sort of thing you can do. Now, once you have these events, you can use them to create storm surges, again, with fairly advanced computer models, which we do have a lot of confidence in. For those of you who've done some modeling, this is the actual lattice or computational lattice that we use in the Gulf of Mexico. I don't know if you can recognize that. There's Florida. We're here somewhere, all right? There's Louisiana. So this is the Gulf. And we run these synthetic storms over the ocean and produce surges. And we can estimate surge risk that way. And in the peculiar case of northwestern Florida, and we think it's peculiar because we don't see it elsewhere, the surge risk you get from the very limited history is very different from the surge risk you get by this technique. In many other places, they're almost identical. So this is the magnitude of the surge. This is in meters. If you multiply by 3, you get feet. So this is about a 30-foot surge. And these red and blue curves are estimates based upon this modeling using somewhat different assumptions in the model. The green curve is what you get from historical events. So according to history, we've never seen in this particular region, you know, a storm surge more than about 5 meters or about 15 feet. But there aren't very many events. That's the problem. The paleotempestology and the modeling are consistent that the real risk is somewhat larger. So an 8-meter surge, you know, is something you might see every few hundred years, all right, which is uncomfortably not long enough. And if you want to wait for 1,000 or 10,000 years, you could see some real whoppers, okay? That's just the nature of it. All right. The final aspect of this that we should all be worried about to some extent is the future. That is, how do we expect this risk to evolve? Well, this same technique I've just been talking about, where you embed a very highly detailed special hurricane model within a global data set, can be applied to global climate models. And we've done a lot of that to try to assess how the risk changes. And this is just a very short tutorial to remind you that the science of climate change, or human-induced climate change, is quite old. This is one of my favorite historical figures, the Swedish chemist Svan Arrhenius, who lived at the end of the 19th and beginning of the 20th centuries, and he was the first to do some calculations that suggested if you change the carbon dioxide content of the air, if you double it, you'd raise the surface temperature by about 4 degrees centigrade, which is well within modern estimates. And he did that without computers, just basic physics, so we don't rely, as some would have you believe, on these. And this is, I think, a verification of Svan Arrhenius's prediction. The blue curve is the observed concentration of carbon dioxide from the late 19th century to the present. It's going up, very robustly measured. The green is the average surface temperature of the planet. There are all kinds of things going on. Some of it is changing sunlight, volcanic eruptions, and just plain random variability. But you can see that on the whole, Arrhenius's prediction is verified, as it should be. It's based on very well-known physics. So the world's warming up. We're doing it. There's not much doubt left around anybody who studies these things professionally. What is it doing to hurricanes? One thing that we observe using satellites is that the latitude at which hurricanes are reaching their peak seems to be increasing in both hemispheres. This is the northern hemisphere. This is the southern hemisphere. This is the latitude at which hurricanes reach their peak intensity. I'm sorry, something went wrong with this slide. This should be about 1980 to the present, going from left to right. And in the northern hemisphere, the latitude's going up, and in the southern hemisphere, the southerly latitude is going up, if you will. And so we do start to see trends in that, but what can we say based on physics? So we're going to take the same approach that we took to assessing hurricane risk in today's climate and apply it to 4 climate models, because we're not all that great at climate modeling. You know, it's enough to model the past, but you know, prediction is very difficult, particularly when it concerns the future, as Niels Bohr told us years ago. And so we did this for Pensacola. We've done it for lots of different places, but I thought it'd be interesting to show you Pensacola. So I'm going to spend a little time on this. We're getting close to the end here. This is, again, return period. Notice it's a log scale, so this is 1 year, 10 years, 100 years, 1,000 years. And then this is the Saffir-Simpson category. This is tropical cyclones, all hurricanes of all category. Category 1, 2, 3, 4, and 5. These are the return periods for today's climate, for these types of storms. And the shading in the background tells you something about the scatter among the 4 climate models. So they take the same hurricane model, but we embed it in 4 different climate models. So today, if you, as I mentioned, if you want to see a Cat 5 within 100 miles of here, you'd have to wait many hundreds of years, about 500 years or so. But depending on the model, this one's like 300, this is 1,000 years, but somewhere in that range. If you want to see a Cat 3 here, as we said before, it's more, well, Cat 4. Ivan was almost Cat 4, by the way, about 100 years or so. And then this is for the climate of the last 20 years of this century, 2081 to 2100. And you can see the return periods have dropped in all the models. So that if you want to see a Cat 5 storm, according to this, you'd only have to wait 40 or 50 years. All right? And Cat 4, maybe 15 years, and so forth. So unfortunately, what this is telling us is that the probability of violent storms in this region seems to be going up with time, according to our best estimates based on physics. Now, we haven't run the surge model for Pensacola, but we've done it other places, and I'm going to talk about my hometown, Boston, which has a lot less hurricane risk than Pensacola, but it's not zero, okay? We have had violent hurricanes in our past, very destructive ones, and this is the same kind of curve I just showed you for the current climate and for the future climate of Boston. But in Boston, we also ran, I'm sorry, I misspoke. This isn't for winds, this is for storm surge in meters. Now, it's a storm surge in Boston Harbor, but it's driven by hurricane winds. And there, the risk of surge goes up. But we didn't, in that calculation, account for the fact that sea level is also going up. This is recorded sea level up until now, and this is projected sea level. These different curves depend upon what we do, whether we try to control carbon dioxide or not. If you account for that, you get huge differences. I mean, surges which are virtually impossible in Boston in today's climate become something that you see every so often. And so we're very worried about that, and so is the city of Boston. And we've tried to use this now. For example, I did a study commissioned by Michael Bloomberg when he was the mayor of New York City to try to understand what this kind of thing would do to damages in the United States. In fact, the study concerned lots of different phenomena, but I'm going to talk about the hurricanes. So this chart shows projected annual costs in 2011 dollars. And this is in billions of dollars, so that's $100 billion there due to hurricanes. And the blue curves are just taking into account sea level rise. So this is the damage due to storm surges. This is the period 2030. This is around 2050. This is the end of the century over here on the right. The green also takes into account changing storm climatology. So by the end of the century, we could be seeing, $80 billion a year on average, not every year, of course, in damages. This is the kind of thing we're trying to do to really put numbers on this. So let me just wrap up. I would say that history, this is one of the main messages I wanted to get across to you because it really affects you. Your insurance rates, everyone's, are based upon historical events, all right? And I think this is very wrong. And it's simply because history is A, short, and B, very imperfect. The hurricane database is a mess, let me tell you. Everybody who works on it will tell you the same thing. We don't actually have very good records of hurricanes, nowhere near what we'd like. And so we're basing our assessment of risk on records that are too short and not very good. We can make better estimates using modern techniques, one of which is based on geology, this field of paleotempestology, which looks for hurricanes in the geological record, okay, and is finding them. And frankly, what's limiting progress is the tiny number of people doing this. So if you've got kids or grandkids who are interested in going to science, this is a hot field to go into, all right, and it's useful. It's really interesting. We just don't have very many sites. I showed you Appalachia Bay. It's also been done in southern Louisiana and up in New England, where I live, and down in Puerto Rico. That's about it around here, all right? Now, not nearly enough to really get an impression of overall climatology. And then the other technique is basically using physics, which is another way of knowing the world, okay? Bringing that to bear in estimating hurricane risk, and I talked a lot about that tonight. And these are beginning to yield some interesting clues about how hurricanes respond to climate and how we can use that to assess risk. So it's very clear from what I told you tonight, but also from a lot of things I didn't have time to tell you, that hurricanes do vary with climate, no matter what causes the climate. They varied between ice ages and interglacial periods. We think there were a lot more and much more violent hurricanes during warm periods like the Eocene 50 million years ago, when there were alligators wandering around Greenland. But also they vary almost certainly with man-made climate change. And we think that there is in certain places, and unfortunately here is one of them, there's a risk that we'll see increased threats over this century. I'll leave you with that slightly gloomy thought, and I'm happy to answer any questions. Okay. Okay, we'll start with the gentleman in the pink shirt there.
Thank you. Going back to that slide that you showed about the historical record that you've determined on hurricanes and periods of high and low activity, does that correlate to anything else in the historical record, like temperatures or atmospheric CO2 or anything that you could draw some conclusions from?
That's an excellent question. I'm glad you asked it. Did everybody hear the question, by the way? I guess the mics are working, so yes, I'll assume that unless I hear otherwise, you've heard the question. There's a lot of work on that, which I didn't show you tonight just from a lot of time. We tend not to look at the kind of records I did show you, which are records at a particular place, because they are subject to just plain random variability. You know, they're just overwhelmed by that. Now, I showed you 4,000 years from that paleotempestology. That is long enough, but we don't have climate data over that period. We don't have a very good idea of what other things like temperature did. So what we do know is we do have records over the good climate records over the last 100 years, and maybe good historical hurricane records over the last 50. And if we don't look at a particular place, but say the whole Atlantic, we do see strong relationships, for example, between the temperature of the tropical ocean in the summer and the power of hurricanes and other signals in other parts of the world. Unfortunately, outside the North Atlantic, which has only 11% of the world's tropical cyclones, the historical hurricane data is really bad. So we're handicapped. But it's a very excellent question. There's a lot of work on it, and I just didn't get around to talking about it tonight. So, okay, how about we move to the gentleman here in the blue shirt? Yeah.
In one of your forecasting models, you had a lot of hurricanes that looked like getting sucked right up into the northern end of the Gulf Coast. Is there any reason for that?
Well, you may be thinking about the graph I showed where I only looked at hurricanes that passed within 100 miles of here. You might be thinking of that graph. That wasn't, so I could have done the whole Gulf, right? And you would have seen a very different picture there. You would have seen a lot of storms going into Mexico. To prepare for this evening, I looked at a set of about 3,500 events that were filtered to pass. You know, they were part of a much, much larger set, but they were only the ones that came close to Pensacola. Okay, we're going to be sort of moving back. So how about the gentleman in the tie there, if you can get to him?
Excellent talk, sir. How much advancement is being done as far as predicting directions? It appears that hurricanes can change directions very quickly. For example, the Labor Day hurricane of 1935, which was a Cat 5, which hit the Keys. And my wife wanted to know also, how did ice form at the top of a hurricane?
Okay, I'll try to do both questions. Hurricanes can take bizarre tracks. One of the ones I remember, I think from the 1980s, that you may remember because it didn't hit this area, but it looked like it might at one point. I think it was Emily. And Emily executed a full loop in the Gulf. And at various times, well, I think if I remember correctly, it was first sort of poised to hit Louisiana, and they evacuated the whole area. And then it turned toward the west coast of Florida, around just north of Tampa. And they called off the evacuation in Louisiana, and they evacuated people from there. Then it did a loop and went back into Louisiana, and they had to re-evacuate all the... So that's the bad news. Those are the kinds of things that keep hurricane forecasters, like in Miami, awake all night, storms like that. The good news is that over the last 40 years, there's been really spectacular improvement in the forecasts of tracks of hurricanes. They've just gotten better and better, and I really mean it. I mean, you look at the numbers, there are enough forecasts that the statistics are robust. The error in the track of the forecast has gone down, down, down. Sandy was a great example. We knew almost a week ahead that Sandy was going to go into New York City. Isn't that amazing? You know, that was a particularly good one, but they are getting better. The bad news is that we're still lousy at forecasting how strong the hurricane will be when it makes landfall. Very little improvement on that. A lot of research, and I have a lot of hope that that's going to get better, but so far it hasn't really. Oh, and the ice, right. So I'm like a cheap hotel, right? No ice. So when you get up to maybe 2 or 3 miles, if I were to launch a weather balloon right now here, right, it's plenty warm at the surface, it may be 70 degrees outside. I only have to go up 2 or 3 miles until I hit the freezing level. And then as I go up higher and higher, it gets colder and colder. So most of the hurricane, which goes up to 10, 11 miles, is in a region below freezing. Now, if you're just below freezing, if you're 10 or 20 degrees below freezing, even though you're below freezing, the water droplets aren't frozen, they're super cooled, which is a big problem for airplanes, because then those droplets will freeze onto the surface. But when you get up to the top of the hurricane, it's so cold, you know, as I said, well below 100 degrees below 0 Fahrenheit. It's all ice crystals. And there are a lot of them. They're very thick. And they actually do pose a risk to modern, curiously enough, to modern jet turbine engines. There are instances of jet aircraft flying into the tops of hurricanes or just ordinary convective systems and losing thrust for some very interesting reasons because they're ingesting so much ice. There's a whole sort of bunch of papers. I'm not an expert at that, but there's lots of ice at the top of the hurricanes. Thank you for reminding me. So let's see. Why don't we go to the woman in the red and white striped shirt?
I like to know, is there any development where you're working on possibly being able to destabilize hurricanes with either chemicals or...
Yeah, well, as I told you, we engineered a little bit of fun and excitement for you today, so we should be able to do that, right? There have been attempts. One of my most famous colleagues who died just a few years ago published a paper in a journal of meteorology, that's what it was called, in the 1950s. I'm not kidding, this is a different era, proposing to blow up a nuclear weapon in a hurricane, which we now know today would have made it stronger and radioactive. So we didn't go down that road. But there were much more serious attempts later on, including an entire project that went on for more than a decade you may not know about called Project Storm Fury, which was conducted by the US government over the North Atlantic and the Caribbean to try to seed the clouds in the outer bands of hurricanes under the theory that you could weaken it. And the problem was twofold. You never could do enough storm. You can't do a controlled experiment. You could never know what would have happened if you hadn't seeded it. So you just have to do lots and lots and lots and then bring in some fancy statisticians and pray. We never had enough. That was problem number one. Problem number two is we were sued by the Cubans and the Mexicans who thought that when they did get clobbered by a hurricane, it was our fault. So that wasn't going to go anywhere legally. There have also been ideas that you could slow down the evaporation of water from the sea surface by putting a kind of a organic oil slick, literally olive oil or something like that. We tried to do that in laboratory experiments. And it works at low wind speeds, but not at hurricane wind speeds. So I think the answer is no. The only technique that poses any hope is to 3 or 4 days ahead of a hurricane landfall is to slightly tamper with the weather upstream of the hurricane and cause normal sort of chaotic air growth. A normal low pressure system like you have every day just happens to develop a little bit earlier or a little bit further along. Nothing unusual, but that would steer the hurricane offshore. That we could do. That's the only promising lead I know about there. Okay, I want to, let's see, let's take one from the front here, and then we'll go further back. So, yeah.
Can you speak to any potential benefits of hurricanes and tropical systems in terms of redistributing heat from the tropics and what would happen if we didn't have that system in place?
Well, that's a very good question. And actually, before I answer the question you actually asked, I'll also say that there are actually benefits to us from hurricanes, direct ones. There are places like the Yucatan where a fair fraction of their annual rainfall comes from tropical cyclones, whether they make it to hurricane status or not. And there are other parts of the world. In Florida, they are sometimes known justifiably as drought busters. You know, the ideal thing if you have a drought is to pray for a weak tropical storm to come ashore and give you enough rain that breaks the dry soil and breaks the whole cycle of the drought. But meteorologically, the tropical cyclones do two rather spectacular things to the climate, to the weather, and that is, it's not that they transport a lot of heat toward the poles directly, but they dry the atmosphere. You can think, well, all this rain, where's it coming from? It's coming from the atmosphere. It's drying it out. And that allows much more heat, because water vapor is the most important greenhouse gas we have. It allows all the heat to escape. So indirectly, they cool the climate. They also churn up a lot of cold water in the ocean. And so you see these spectacular cold wakes that are generated by the storms that do all kinds of interesting things physically and biologically. They also bring nutrients to the surface. So you get big phytoplankton blooms. So in Taiwan, they go fishing in hurricane wakes 3 weeks after the storm. And that's a tip for you fishermen, right? Wait for 3 weeks after the hurricane and go fishing. Just make sure there's not another one coming. But they also cause ocean currents that transport heat. That's a little bit more complicated. So we're just beginning to figure out what they're doing. They're kind of regulators of the climate of the tropics. Yep. So, okay.
I've done some of my own research, and after seeing the climate change and the rise in sea levels and increased carbon footprint, I decided it would be a good idea to start building hotels on the beachfront. That would be a good long-term business model. But what my question to you is, we do a lot of borings when we build the hotels, and we go down 60 feet. Could you use these borings to do some of your study on historical hurricanes?
I think it depends critically on the particular location of the particular building you're building. So if it's straight sand, probably not, because we need the mud. We need the mud background, basically. Okay, so if you have a place, you know, that's sort of swampy and muddy, but it's close enough to the beach that storm surges could affect it, yeah. We can talk about that. I can put you in touch with the people who'd love to get their hands on those cores. Okay, well, we'll take one more from the front, and then we'll go to the back of the room.
It was an excellent discussion up to this point, but I'm kind of curious as to what, in the lines of forecasting on the immediate level, that we have available to increase maybe the accuracy, because I notice we adjust as we go through the year. And the only reason that I say that is I noticed something peculiar when I came into this area. It seemed as though during the season 4000, 4005, we had almost like an early warning with the massive accumulation of precipitation that we had prior to or going into the hurricane season, which followed by an immense amount of hurricane activity. And I don't know if that's got anything to do with it, but after 60 years of flying, it helped keep me alive.
Well, that's another interesting question. There are folks who are trying to do seasonal forecasts of many things, like rainfall and hurricanes. And so far, we haven't gotten very good at that. There's some hope for it. I'm a little bit pessimistic. There are certain things we can say. For example, a year ago, a little less than a year ago, when it was very obvious that we were going to have a spectacularly big El Nino this year, which we had, we could say with some confidence that it would be a quiet Atlantic hurricane season, which it was. There's a very well-known relationship between Atlantic hurricanes and El Nino. El Nino suppresses them. And so that's one signal we can use. And it's not foolproof. Andrew, which at the time occurred was the most expensive storm ever anywhere in the world, occurred in an El Nino year. And it was a very quiet year, actually. There were not very many storms that year. It only takes one. So you have to remember that, never to let your guard down when it comes to hurricanes.
We have time for one last question.
Okay, well, how about we go to the man right there that you're standing next to? Yes.
I have two questions, one a little more serious, one a little lighter. On the more serious note, you talked about the wind speeds, and we've heard a couple of people mention about moving and building near the beach, etc. People are now trying to live closer to the beach and closer to the water than they did 100 years ago. And in doing so, the impact of both rising water temperature and man-made effects on depleting barrier islands, which reduce the wind speed. Would you like to comment about that at all? And that's the serious question.
Okay. Well, your question is the thing that many people in my profession spend the most time worrying about. As we have two trends that are aligned to give us big problems in the United States. Well, there's one that's global, and the global one is, as you point out correctly, demographically, there's a migration of people from inland to the coast. Right? It's all over the world, not just here, but it's certainly here. And that makes people more, that puts more people and material in the way of harm from hurricanes. And the other problem is that's not colliding with the problems I talked about tonight of climate change and sea level rise. And so we're very, very worried about that. Now here in the US, the problem is very much wrapped up with policy. We strongly regulate property insurance in the United States, probably more strongly regulated than any other industry. And we cap insurance premiums, and we provide federal flood insurance whose premiums don't begin to cover the risk. And so we have a problem, and you won't like to hear this in this audience, but it's the truth. Inland people are subsidizing people on the coast massively. And that's leading to a lot of building on the coast. So people are, when you subsidize people to do that, you can't blame them for doing that, right? I'd build a condo if I had the cash on the beach too, even though I know it's foolish, because it's much cheaper than it should be. So what's your lighter?
On the lighter side, you started off talking about the derivation and origination of the word hurricane. And what was it, about 20 years ago when they started naming them after alternating men and women? But the original
70s,
hurricane,
yeah.
would you like to comment? It was originally called a hurricane because no man could do that much damage?
Yeah, it actually, the practice, I won't launch into a long thing about this. The practice of naming storms, we think hurricanes actually started in Australia. And here's the part I love. You know what they did? And it wasn't gender selective at all. They named them after politicians. Yeah. Now I think we should go back to that. I'll end on that note.